We're going to be talking about selecting a buffer and something called buffer capacity. So when we think about a buffered solution, so a buffered solution resists a change in pH because it's got a weak acid and its conjugate base. So when we're selecting a buffer, we're looking for a few things. We want large concentrations of both the weak acid and its conjugate base, or a base and a weak base and its conjugate acid. Um, we want the concentration of HA to be roughly equal to the concentration of A minus. And this helps resist changes from acids and bases. So if our HA over A minus, or HA is roughly equal to A minus, that means that the log of base over acid, which you'll recognize from Henderson-Hasselbalch, that's going to be the log of 1. That's going to be pretty close to the log of 1, which means that that's just going to be 0. And if I write out the full Henderson-Hasselbalch equation, pH equals pKa plus log concentration of base over concentration of acid. Okay, so if our log of base over acid is just 0, then that means that pH just equals the pKa of the acid that we're talking about. Okay, so let's say, for example, that we want a pH of 4.30. Okay, well, if we're selecting a buffered system, we know that we want the pH to be about the pKa. All right, well, Ka equals 10 to the minus pKa. And I'm going to convert this to Ka because the acid strength table is generally organized by the acid ionization constant, Ka. And the pK is not generally given. All right. So we're looking for a Ka value of 5.0 times 10 to the minus 5. So I'm going to go over to my Zumdahl chapters, and on one of the last pages of the document that I gave you, there's this values of Ka for some common monoprotic acids. So I'm looking for something around 5.0 times 10 to the minus 5, so that looks like benzoic acid would be a good choice. Okay. Okay. Now, so we know which acid we're going to use. Now we need to figure out the ratio of the acid and base, what ratio we need. So we'll start with we're going to start with Henderson, Hasselbeck. And then we're going to subtract pKa. So pH minus pKa equals log concentration of base over concentration of acid. And then I'm going to anti-log both sides. So 10 to the pH minus pKa equals concentration of base over concentration of acid. So in this case, we're going to take, by the way, the pKa of benzoic acid and that's going to be 4.19. You can do that math. You just take the Ka and take the anti-log of it. Okay, so now we have 10 to the pH that we're looking for, 4.30, minus the pKa, which is 4.19, and that gives us 1.28. Okay, which means that I'd be looking for about a 1.28 molar solution of base to 1 molar solution of acid. Okay, so remember that this is giving us a ratio. Okay, so how does this work? Well, let's compare a good buffer, which is this 1.28. So we're going to compare a benzoic acid to, I'm going to do nitrous acid. And I'm picking nitrous acid because it's here on the list. It's not like crazy far away, but it's still pretty far away. And we'll see the difference. Okay? So if we do, we already know in the benzoic acid solution that it's 1.28 molar benzoic acid, of the base, which is benzoate, to the acid, okay, those are the ratios that we're going to use. And we're actually going to use 1.28 molar and 1.00 molar. Now, when we do the 10, when we do the ratio, so A minus O over HA is 10 to the pH minus pKa. When I do that for nitrous acid, what I get is 7.98 molar to 1 molar. Okay, now in order to keep this relatively fair, I'm going to max out at around 1 molar. Okay, so we're going to do 1 molar of this to 0.13 molar of the acid. When I do the actual pH of this solution, okay, the 1.28 and the 1.00, I get a pH of 4.301. And I'm leaving a whole bunch of decimal points because they're kind of important. Now, if we take the pH of a solution that has 1.00 molar nitrite ion and 0.13 molar nitrous acid, if I find that pH, I will get a pH of 4.284. And I'm just using Henderson-Hasselbalch for that. So now the question becomes, what happens if I add 0.05 moles sodium hydroxide to each? Okay. So the first thing that's going to happen is that sodium hydroxide, that's going to fully dissociate. So you're just adding a bunch of hydroxide ions, and the hydroxide ions going to react stoichiometrically with the weak acid. Okay, so that's a Rice end table for each, where the acid reacts with sodium hydroxide, the hydroxide ion, to make water plus the base, the conjugate base. Okay, so we're starting with, remember this one needs to be in moles, but I'm going to do to 1 liter of each solution. Okay, and that'll make my calculations a lot easier. That way, the molarity and the moles are equal numbers. Okay, so 1 mole HA, I'm going to add 0.05 moles sodium hydroxide. This is for the benzoic acid. And then I have 1.28 moles of the anion to start with. Okay, and we know that this reaction is going to go forward, and that's going to be our limiting reactant. So we're going to go down by 0.05. We're going to add 0.05 moles to this side. So we get 0.95, 0, and 1.33 moles on that side. Okay? Now I can do the same thing for the nitrous acid. Okay, now the next thing that we would do is we would do the Rice-EQ table, so the equilibrium. And I'm just going to do it for this first one, and that'll make sense in a minute. So our equilibrium looks like that. We start with these. Now I've turned these back into concentrations, right? So this is now in molar. So you got to be a little careful with that, like when you're going between the steps. But I have 1 liter of solution. That makes everything much better. Now, the reason that I'm only going to do this once is because we're going to be making the assumption that this is just 0.95. And this one's going to go up by x, making it just x. And this one's also going to go up by x, but we're going to make the assumption that that's just 1.33. Okay, now I have my concentration of the concentration of acid and the conjugate at equilibrium. So now I can just plug that into Henderson-Hasselbalch. And I'm doing the negative log of Ka for that, just to get that value. So when I do this, I get 4.33 995. Okay, so the change from the solution, remember I calculated the pH of the solution earlier was 4.301. Now it's 4.33. That's not a big difference. That change is 0.0389, which we'll just call 0.04. Okay, not a big change. This is a good buffered solution. All right, our pH is close to the pKa. Our concentrations of acid, both acid and base, are really large. So let's go take a look at the one that's not as good of a buffered solution. Okay, so I'm not going to repeat this RICE-EQ for this one. We can just jump straight to Henderson-Hasselbalch because we're going to still make the assumptions that we made in the last one. Now this one's got a different K value. .516. So when I do the change of this one, going 4.516 to 4.284, that change is 0.23. And that is a much, much bigger difference. Okay? And the reason that this is not as good of a buffer solution is because our pKa, our Ka value, is not close to the pH, which means that we need to have kind of, we end up having a very small concentration of our HA. So even though it's changing by the same amount in both cases, right? The concentration of the weak acid is going down by 0.05 moles. This is a much bigger percentage change than this, okay? So this one has a greater effect on the ratio in Henderson-Hasselbalch. That's why you look for um, a acid weak base, or sorry, weak acid base pair where the pH is close to pKa, okay? And that is selecting the correct buffer for a solution.